Alright, today's lesson is going to be on Coulombs Law. Coulombs Law is doing nothing to it but referring to the fact that opposites attract each other. So that's what we're looking at here. Opposites attract, like charges repel each other. It's just that now we actually have an equation to calculate that force of attraction or repulsion. So in this case, the Coulombs Law in an equation is F equals K Q1 Q2 over R square, where K is given a value of 8.99 times 10 to the 9. Now, for the most part, AP is going to use 9 times 10 to the 9 for that, but what can I say? I'm still using 8.99 times 10 to the 9. Now, the two Q's are just going to be any two charges, protons, electrons. If you would just remember that the charge for a proton or the charge for an electron, they're both going to be equal to 1.6 times 10 to the negative 19 coulombs. And you'll use that in a lot of these problems that are in here. The first problem I want you to look at is a problem that's called a well, it turns out somebody walked off with that page that had that first problem on there. But anyway, I'm pretty sure the first problem, example A. Too bad I can't pause this video. Stephen, any chance you'd go in the lab and look for a sheet of problems like this? Thanks, old man. Example A, though, wants to know the force of attraction between a proton and electron inside of a hydrogen atom. So if we say, okay, here is our proton with a positive charge, here is an electron with a negative charge, there's going to be a force between those. We're going to have a force pulling those two particles together. We'll call this the force of the proton on the electron, and this can also be the force of the proton on the electron. It even gives us a distance of separation. To calculate that electrostatic force, we'll just apply Coulombs Law. K, and I'm not going to write out 8.99 times 10 to the 9. Whenever I write K, you know, I expect you to know what I'm implying. So K times 1.6 times 10 to the negative 19, the charge of a proton. Well, and since that's also the charge of electron, and we've just got Q times Q, we'll just write Q square up above that. Underneath, the example says that they are separated by a distance of 5.3 times 10 to the negative 11 meters. Put that down here, square that, and you should be able to get a value for that now. Now, one of the other questions that it asks, it says also, it said to calculate this electrostatic force, but it also wants you to calculate the force due to gravity between those two. Force due to gravity, of course, is given as big G M1 M2 over R square. Now, I hope you notice that there are definitely some similarities between these two equations. Both of these collectively are known as an inverse square law for that reason. As the separation between the particles or the masses increases, your force falls by square proportion. So that's just a little neat thing. That's why these two look eerily like the same equation. So in this case, we'll go big G, which if you've forgotten what big G is, it's 6.67 times 10 to the negative 11. Big G times the mass of a proton is 1.67 times 10 to the negative 27, if my pen will write. The mass of an electron is, good answer, 9.11 times 10 to the negative 31. We'll put all that over, again 5.3 times 10 to the negative 11, square it. Now, when you get your answer for this force of gravity, compared to this electrostatic force, gravity is a much weaker force. Fundamentally, gravity is indeed a weak force. We only think of it strong because we're sitting on top of a 5.98 times 10 to the 24 kilogram object. But you'll notice that the electrostatic force is actually much stronger. And what's funny is, in terms of how strong it is, the nuclear force, which exists inside of an atom, is actually even far stronger than either of these two forces. So, anyway, which explains why gravity is not what holds an atom together. Its electrostatic forces should force it apart. But anyway, that was how you do example B, or example A. Now let's take a look at example B that was given you. All right. So to do example B, and let's take a look. We've got a little simple drawing here. We've got a negative particle here. We've got a, I need to definitely rearrange my paper a little bit more. There. We've got a negative particle here. We've also got a positive particle down here. We've got another positive particle up here. And we've got a perfect little 3, 4, 5 triangle here as well. And let's keep that in mind because often in the AP we have 3, 4, 5 triangles. So 3, 4, 5. It's even been kind enough to go ahead and let us know that this up here is a 37-degree angle. Now, the pictures already give the forces on there, but I want you to understand where those forces came from. These two objects are both positive, so what kind of force are we going to have between them? Positive, positive. Those two are going to repel each other. All right, this charge, let's see if we can get this. Q1, the charge down here, Q1 is a 6 nanocoulomb charge. The negative charge, Q2, is a 2 nanocoulomb charge. Now notice how I didn't write down negative 2. The only significance of the negative sign is that's going to tell us which direction this force is going to be located. Alright, and then this charge we're actually looking at, Q3, is a 5. And I'm going to kind of write it down here out of the way. A 5 nanocoulomb charge. So these two particles are going to exert forces away from each other. So I'm going to draw an arrow up and away up here. And I'm going to call that force of 6 on 5, which means we would also have that identical force down here for 6 on 5. This is a positive and a negative, which means those two are going to what? Exactly, they're going to attract each other. So up here we're going to have a force. Here we'll call that force 2 on 5, and that same force would also be present here, a force 2 on 5. So the first thing you would need to do to work this problem is calculate what these two forces are. To do that, we'll just use Coulombs Law. We know that force is equal to what? K, Q1, Q2 over R squared. So we know K, 8.99 times 9, and we've got a 6 nanocoulomb charge and a 5 nanocoulomb charge. Now I'm writing out these ends, but make sure you remember when you put them in your calculator, write 10 to the negative 9 over 5 squared. Get that value. That's for F6 on 5. Now for F2 on 5, it'll be the same thing. K, 2 nanocoulombs times 5 nanocoulombs. Again, don't forget your nanos. These are going to be very small values. Over 4 square. Now, once you have your two values on this, what we're going to be left with at that point, see if I can get my paper the way I wrote it here. We're going to know the forces. Now I want you to look at what we're going to be left with at that. We're going to have this charged particle. We're going to have a force 6.5 in this direction and a force 2.5 in that direction. if you're thinking to yourself, this is a hiker in the woods question or a stoplight type thing, you're right, it's a hiker in the woods. We're going to do some of the forces, and we're going to find the resultant, and we're going to find the angle. Sum of the force is x, and I don't have the numbers calculated, so I'm just going to write it out like an equation. Sum of the force is x would be F65 cosine of 37 minus force 25. We get that value. Sum of the forces y would be equal to, well, F65 sine 37, and this one doesn't have a perpendicular component, so that's just equal to, not 0, but equal to whatever it's equal to. So you should have a value here and a value here. Now I'm going to bet that when you get these two values, just from looking at the numbers, you're probably going to have a little short over and one up. This is, again, my guesstimation. So I want you to find that resultant, r equals square root of x squared plus y squared. And I want you to also find that angle. Theta would be equal to tangent -1. Tangent -1 over a. Thank you, Stephen, for pointing out I'm off the page. So, anyway, so notice something. This has become a typical hiker in the woods type question. And that's the way all these become. Some of the later ones are even going to be easier. Some of these other examples that they want you to work in, my light's just motion censored off. Stupid lights. Some of these later problems, they're going to give you something like this. They're going to give you a particle here, a positive, and they might put a negative over here, and a positive over here. We'll call this 2 nanocoulombs. We'll call that 4 nanocoulombs, and let's go crazy and call that 6 nanocoulombs. And it'll say, find the force on the 4. Well, what kind of force do you have between the 4 and the 6? Those two are going to attract each other. So you're going to have a force of 4 on 6 going that way, and then you're going to have a force also, if you notice, these are positive, so is there a force in this direction, in the negative x? No, there isn't. So both your forces, the 2 on 4, is also this way. So in this case, find F46, F24, and you've got your answer for this one. Again, just use the Coulombs Law to find all these answers. You can do, at this point, 1 through 12 on this page. And some of them are going to be kind of easy, and a couple of them, though, if there's any angles in there, it's going to turn into this resultant question where you're going to have to work it out like this. So, if there's no further questions, have fun. Adios. Just stab myself.